Hello and good day to all of you. So in this video lecture, we are going to learn about the machine learning algorithms, specifically for the supervised machine learning. So as we know that there are different type of machine learning algorithms. So just a quick review of the previous talk. So in this, we have supervised machine learning, unsupervised reinforcement, and semi-supervised machine learning. So today we are going to look at the supervised machine learning and the algorithms which we are using for performing the supervised machine learning. So let's get started. If you look at the supervised machine learning algorithms, so in this we have multiple algorithms which you have been learning around the world. So the first one is the linear model. So in models, we have regressions, we have classification, regularization. And also in the supervised machine learning, we have the k nearest neighbor, KNN, support vector machine, stochastic gradient, decision tree, ensemble learning, generative models, time series forecasting, supervised dimensionality reductions technique. So these are actually the 9 machine learning algorithm which is used for supervised machine learning. So today we are going to start with the linear model. And in linear model, we are focusing on the regression in this part of the lecture. So if you look at the regression, so there are different type of regression models. So it's almost 10 type of regressions machine learning algorithms. So in which the number one is the ordinary least square regression. The second one is the simple linear regression. Then we have multiple linear regression. And also we have polynomial regression. Let's say if you have multidimensional. Then we have another type of algorithm which is called orthogonal matching pursuit algorithms. Then again, we have number 6 is Bayesian regression. So in this, it has the prior knowledge then applied to the Bayesian regression. Then quantile regression, isotonic regression, stepwise regression, and least angle regression. So these 10 number of algorithms which we are going to discuss in this part of the lecture. So let's look at the first type of regression, so which is ordinary least square regression. So this is actually the regression. In this regression model, it established the relationship between the dependent variable, which is y, and at least one independent variable. So let's say this is the y cap is equal to b1x plus b naught. So this is the dependent variable, and these are the independent variables. And also OLS, which is the ordinary least square regression, in which we have to choose the value of such as b1 and b0, such that the total number of square of the difference between calculated and observed values of the y is minimal. So in this, a simple method is that's what we have to do. We have to find the difference or between the actual values minus the predicted value. We take the square of this one. So these are the parameters you can look at. And further, what are the modules which we use for the OLS regression? So in this Python library, we have these state models, so which provide the classes and function for the estimation of the many different statistical models for ordinary least square migration. So just an example over here. So you can see ordinary least square regression, which is a very most popular techniques for estimating the coefficient of the linear regression equation, in which it describes the relation between one or more independent variables. Let's say this is one dependent and independent variable. So also you need to calculate the difference between these things. So obviously on the left side figure, you can see this is the y and x. So we have the point data, but over here the regressions pass through here. So ordinary least square regression is actually the methods of calculating the real, which is the obs observed data, and this is the predicted data. So the objective of this algorithm is to find the difference between these two. Over here it is also, you can see these red points are actually the predictive observed value, which is the actual value, and the white dots are actually the predicted value because it's passing through these regression lines. So we have to find the difference between this one and this one. So based on that, we can have the y and x value and the difference between these two. So by using the previous equation. Another representation of what is the difference between OLS and the linear regression, which we are going to discuss in the next part of this next type of the regression. So over here, actually, in the least square method, what you do, actually, you have the data points, let's say these one. So you pass the linear regression, which is this red line. So the difference between this red line and also the ordinary least square regression is you find the difference because the actual point is here, but your regression line is passing from here. So the value which is coming from this y and this x has to be find the least square error. I mean the error from this point to this point. So once we have the values, let's say the y and this is the xi, so we can put in the formula, which is this one summation y, which is the actual value, and y cap is the predicted value whole square. So this is how the OLS or the ordinary least square regression methods work. So over here in this, you can see this is the regression line, but the actual points are here. So regression line is explained by y is equal to a plus bx, but the least square regression is represented by this equation. So in this, we have to find the difference between the predicted and the actual value. So let's look at the simple linear regression, which is the second type of supervised machine learning algorithms in the regression section. So in simple linear regression, which is the common method which we normally use. So in this method, it belongs to the statistical subject, and it is used to predict the continuous dependent variable just at the target variable based on one or more independent variables. So in this, you have one dependent and one independent variable. So you have the data points, and what you have to do, you have to just pass through the best fit line, and you will find the simple linear regression, or how the data points are generally aligned based on the linear regression. So there are different data example is shown here. So this is the first example. In this, you can see from this data, it's a linear regression. So in this, obviously, the data does not follow. If you pass the line from here, it doesn't pass through. It can be linear regression, but actually for this type of data, we use another type of regressions, which we are going to discuss in the next slides. And also this is, again, this non-linear data. So the linear data has two types. So one of them is simple linear regression, and the second one is a multiple linear regression. So in simple linear regression, it's involved predicting the dependent variable based on a single independent variable. Let's say you have x and y. So this is one of them is dependent and another is independent variable. So based on that, you can plot the data points. Let's say x is here and y is here. So you plot the data, then you have to pass the best fit line from these points. So this is the simple linear regression. So the multiple linear regression is actually belongs to the another type. So let's look at that one. So this is a type 3 of the regression part, multilinear regression. So in multilinear regression, it's actually involved predicting a dependent variable based on the multiple independent variables. So like here we have, let's say there was only one dependent and one independent, but in this case, we can have multiple independent variables. So in this case, we represent our data in the form of feature matrix like this. So in this, you have x11 and up to xn1, which is represent n into p, which is the number of row and number of columns here. And also there is another responsive vector. So one of them, which is the independent variable, is represent as x, and y is the responsive vector, which is represent as one column. So in here we have multiple variables, but here you have the one variable. So this will depend on these independent variables like that. So it can represent, obviously, if it is multidimensional, and obviously if we have multi data. So let's say in this, we are having one of the example from the groundwater level change, and also the ground level depth. What is the depth? What is the water level change? And also the land velocity. So we have three component. So then we plot it into this form. So you have the data points and you find the regression line on that. Similarly, here is one of the example is from horsepower, weight, and also MPG. So if you have a multiple data point, then you can pass through this linear regression, multiple linear regression. So let's look at the fourth type of regression analysis, which is called the polynomial regression. So polynomial regression is a form of linear regression where only due to non-linear relationship between the dependent and independent variables. And also we add some polynomial terms to the linear regression to convert it into the polynomial regression. So it is normally the simple linear regression, but we add some of the thing. So there are some steps. Let's say we have to visualize the data first. Then the second thing is you have to apply the linear regression. So the data looks like this. So when you pass the linear regression, so you think that this is not rightly mention or represent the data points, because the least square error is too much from here to here and from here to here and also here to here. So it is not the best representation. So what you do in the third step, you apply the polynomial regression. So in polynomial regression, so you can see the points which is matching to this red line, which is the um, predictive polynomial regression. And also further, if you want to play with the polynomial degrees, like if you have different degrees of the polynomial, so it will represent the best points or the best passing through the points, which is called degree 25. So in this, normally you have the data, then you have the polynomial transform and linear regression, then you do the prediction. It can also represent in 3D form. So let's say if you have a 3D data points similar to the linear regression. So you have these points which is passing through this linear regression. Then after you apply some adjustment to the polynomial regression, so you can find. So normally this is used for the surface creation or the horizon mapping in the geophysics as well. So another type of regression, which is the fifth, orthogonal matching pursuit. So the orthogonal matching pursuit is an interactive algorithm used in compressed sensing for sparse signal recovery. And it is a greedy algorithm that seeks to appropriate a sparse signal by selecting a subset of the signal from a given dictionary that best represent the signal. So normally it is performed in different type of steps. So we have explained in the 6 steps of this algorithm. So the first step in this algorithm is initialization. So in this procedure, it sets the residual as the original signal and initialize an empty support set they store indices of the selected atoms. So I will explain, I will give you an example of these steps. Then it has the iteration, so it's repeat the following steps into desired stopping creation is met. So in which, for example, we have the maximum number of iteration or the threshold on the residual error. Then there is another procedure which is atom selection. So it's compute the inner products correlation between the residual and the atom in the dictionary. So that is one of the selected the atoms with the highest absolute correlation and indices to the support set. Then this is a projection, the fourth step. Then after that, we update the residual error or the residual of what happened, whatever is left out in the signal, then we reconstruct the signal. So from the verbally, it is a little bit confusing, but if you look at the example here, so in this actually, it is applying to the one of the signal. So let's say you had the signal, which is shown in this red dot. So it takes the point here and it's generate using the orthogonal matching pursuit algorithms. So based on that, then it's try to adjust these points, which is actually the relative retired coefficient of this retrieve coefficient of the matching pursuit. So from there, you can see matching pursuit is the orange waves is matching to the original wave, which is given in this part of the waves. Also, some of the application of this matching pursuit algorithms in the seismic field. So on the left side, you can see the synthetic seismic data, and here is a different, the data representing the frequency spectrum of the 15 Hertz. But here you can see a lot of artifact which is produced because of the single channel least square matching pursuit method. But when they use multi-channel matching pursuit method, then you can see though the waves, over here the wave was not matching, but when they use multi-channel matching pursuit, so you can see the accurate matching of the wave, and you can see the best signal approach over here and also in this part. So the sixth type of the regression analysis is the Bayesian regression, which is one of the more important regression analysis. So let's look at what is the Bayesian regression. So Bayesian regression implies the prior belief or the knowledge about the data to learn more about it and create more accurate predictions. It's having the experiences from the before, and whatever in our machine is learned from the previous information, so it will use that information and try to predict your results. And it also takes into account the data uncertainty and leverage the prior knowledge to provide more precise estimation of the data. So as a result, it is an ideal choice when the data is complex or ambiguous. So also, if we know that the Bayes theorem, which is mostly used in the Bayesian algorithms, so it estimates the likelihood and the set of parameters given observed data. So what is the difference between the traditional linear regression and the Bayesian regression? So if you look at the traditional linear regression, it actually follows the Gaussian or the normal distribution, but the Bayesian regression has a strong assumption that the nature of the data and put the prior probability distribution of the parameters. And also it's provide the more accurate predictive measure from fewer data points, and it's able to constrain estimate for uncertainty around the estimate. So let's look at the understanding of this method, which is the Bayes theorem. So Bayes theorem actually gives the relationship between the even prior probability and the posterior probability after the evidence is taken into account. So probability of A, that is B, probability of B, or it can call probability of A being true given the B is true. So in this, it is depend on the B and A, and also probability of A divided by probability of B. So this is called the posterior probability, and this is likelihood, and prior, and this is the marginalization. So now let's look at these two methods, which is the maximum likelihood estimation and the maximum posterior or the posteriori estimation, which is the MAP and ML. So the first method, which is use the likelihood, is incorporate the prior information or the assumption that the parameters provide the points. But in this maximum posteriori estimation, actually it use both the prior information and also the likelihood function. So the difference between these two is actually the MLE use likelihood, and MAP, which is the posterior, which normally use the Bayesian algorithm, it use the information of the prior and the likelihood. So the Bayesian regression give you the more accurate results based on the likelihood and also the prior information, which is in the machine. So where we can use the Bayesian regression? So there are several reasons why the Bayesian regression is useful over the regression techniques. Some of them are as follow. So the first of all, the analysis involves the prior belief about the parameters. So it's also useful data and the prior knowledge matters. The Bayesian regression calculates the regression parameter more accurately by mixing prior knowledge with observed data. And also the Bayesian regression generates the posterior distribution, so which measure the parameters uncertainty in a natural way. And also it's provide the flexibility by offering the framework of integrating the various prior distribution handle complicated correlation or nonlinear. Even if standard regression techniques such as linearity is also assumption the false, and it allows more realistic and complex predictors responsible variables modeling. So it is also used for the posterior probability to help choose and the compare the model. And also it is used for outliers and influential observation better than the conventional regressions. So that's why we use the Bayesian regression analysis for this type of application. So what are the disadvantages of this Bayesian regression? So the first thing is that it inference the model can be time consuming. Obviously, if you have a prior knowledge, posterior knowledge, you have to predict the posterior knowledge based on the prior and likelihood method. So it can have more time consuming. The second thing is if there is a large amount of data available for our data set, so this approach will not be worth to use it because the regular frequentist approach does a more efficient job for training the model. So the third thing is that if your codes is in setting where the installing a new packages is challenging, then there are strong dependency control. This might be an issue as well. And also there are many basic mistakes that commonly plug traditional frequency regressions model still apply to the Bayesian model. So for example, Bayesian inversion model or Bayesian regression models still depends on the linearity of the relationship between the characteristics and the outcome variables. So there are some hints why or when we use the Bayesian regression. So the summary of this Bayesian inversion is that we can use the Bayesian inversion when we have the small data set and we have the tiny sample size. So this will be very helpful. And in fact, it is probably the greatest choice you have. The large sample size necessary for many other machine learning models to work properly. And also the second thing is strong prior knowledge. So if you have the strong prior knowledge in the data, then it is easiest method to include the strong external knowledge into your model by utilizing the Bayesian models. And the inference of the prior knowledge will be more obvious the smaller the data size you have with. So how does it work? So we have the belief about the world. So what are the real facts? And we collect the data. I mean, this is the prior knowledge, and we collect the data and create the models. So it will depend on the data and also the prior knowledge. Then it's update the Bayesian models, which is the Bayesian update. Then again, it will go for the belief about the world, or either it starts from here, or it's like a never-ending cycle. So if you look at the graph, so in this you have some of the, this is the likelihood method, this is the prior model, and this is the posterior regression analysis. So the seventh type of regression is quantile regression. So quantile regression is a simply an extended version of the linear regression. So quantile regressions constructs a relationship between the group of variables, also known as the independent variable, and also known as the percentile, like dependent variable. So it actually predict the percentile. Let's say if you have the data from 10 years, so what will be in the next 5 years? So it will be depending on that type of applications. So for example, let's say distance travel as a predictor variable, and the mileage achieved is a responsive variable. So we have the data, let's say this is the distance travel and this is the emission generated. So we have this data, so we can pass through the regression analysis and we can predict the future prediction of this data. So over here is a nice example. So shows like we have some time here and also the demand. So the observed past data which we have in this form of the curve. So this is the past and we can predict the future. So which is based on the different percentile. So let's say if we based on the observed data, the past data, we can predict the 75% of the quantile. So it will goes up to like that. And the 25% of quantile, it will shows the curve like this green color. And we can also find the mean in between that. And also the quantile gradient, which normally boost from here. I mean, let's start from here. So if you have the data here, which is the random forest, and this quantile regression, so looks like this one. So the eighth type of regression is isotonic regression. So the isotonic regression is, or we can call it a monotonic regression, which is a technique of fitting a free-form line to a sequence of observation, such as that the fitted line is non-decreasing or not non-increasing as well. So it can apply to the everywheres and lies as close to the observation as possible. So over here it is very well representatory in the data set. So the equation looks like this one. So minimum summation I wi. So the actual minus observed square. So we have the data on x and y. So you can see that if we have this data point, which is in the training data, which is the blue point. So we pass the linear regression, which is the green color, linear fit. But when we try to look at the isotonic fit, so it's depend on the near data. Like the data points are here, so it will have like this type of this type. So in finally, you can see the isotonic regressions look like this one. So it is more accurate and predict the more close data. So there is less chance of the least square errors. So the linear, what is the difference between linear and isotonic regression? So linear regression used at a least square analysis at all the points at once, but the isotonic regression use a least square analysis of the group of points so that each group supplies a point that does not contradict the formula which is given in this xi is less than xi plus 1. So over here you can see the linear regression if we have this form of the data. So let's say the data points are here, over here. When you put the linear regression, you will pass through this line. But in the logistic regression, which is one of the another type, we are going to discuss later on. So this is passed through like that one. So which is the sigmoid, like that. But in isotonic regression, you can see this data is passing through the different points. So you can put the isotonic regression, one is here, then one is here, like that. So the application of the isotonic regression is used in the probabilistic classification of calibrate the predicted probability of supervised machine learning model. And it has been used to estimate the continuous dose response relationship in the field of anesthesiology and toxicology. So the second last type of regression is the stepwise regression. So this is actually the very simple regression. So it is used step by step iterative construction of the regression model that involve the selection of the independent variables to use the final model, and it involves adding or removing the potential explanatory variables in the succession of the testing of the statistical significance after each iteration. So you can see the basic stepwise process. So you have the stepwise process over here. I have another example in the next slide. So in the simple steps, what you have the number of sample data, which is number of variable. So in a stepwise regression, what you do, normally you find the best sample which you think is better for you. So this is coming from here and this is coming from here. So normally in this, your sample size is actually greater than the number of variables which you have the more generated model. So the advantages of this stepwise regression is provide insightful into the data and also easy to implement. It saves the time and resources and also improve the model performance because you will discard the other data which is not required for the model creation and identify the most relevant features. So obviously there are some types of the stepwise regression. So first of all is the forward selection. So in forward selection, the algorithm starts from an empty model. So over here, you have the empty model and iteratively adds the variables, such as you can add one variables over here, then until no further improvement is made, like the second variable. So the second type of stepwise regression is the backward elimination. So in this, normally your model will start with the filled model, the full model, and include all the variables, iteratively remove until no further improvement is made. So let's say in the first steps, the model with 4 variables, so you will remove one. Now we move another variable, so you will left with the 3 models. So the last but not least is the least angle regression. So it is also known as LARS. So in this linear regression or the least angle regression, so it is actually approached for high dimensional data. So the least angle regression resembles the forward stepwise regression. And in the data, many properties determine the attribute best associated with the goal values at the each stages. The multi-attributes may correlate. And also in this type of regression, the approach is named least regression without overfitting the models. So least angle regression leap in the best calculated direction. So over here you can see you have different directions, like you have x, you have 2y, 2x, and you have mu as well. So they are multi-dimensional data. So what are the advantages of this least angle regression? So it's computationally as fast as the forward selection, but may sometime be more accurate. So it will be more accurate than the fast or the forward selections method. And numerically very efficient when the number of the feature is much larger than the number of the data instance. And it can easily be modified to produce solution for other estimators. So also there is some disadvantages, but not many. So LARS is or the least angle regression algorithm is highly sensitive to the noise and can produce unpredictable results sometimes. So with that all, thank you so much. And in the next lecture, we are going to look at the further classification of the supervised machine learning. In the supervised machine learning, we have covered the regression. So in the next, we will cover the classification and so on. So with that all, thank you so much and have a good day.